Hello everybody, welcome to my presentation. I will give you a brief overview on our work about error-and-erasure decoding of product and staircase codes with simplified extrinsic message passing. I'm Cici Miao, and this is a joint work with Lucas Hub and Laurent Schmalen. We start with a brief motivation. We know that product codes and staircase codes, they are powerful code constructions, and conventionally they are decoded with the efficient IBDD decoders. But recently we found that if we introduce a small amount of soft information to aid the IBDD decoder, we will have much better decoding performance, but the complexity can be kept similarly low as in the IBDD decoders. And the key problem is how do we introduce the soft information and what form should we take? We focus on error-and-erasure decoding mostly because of two reasons. So first of all, these additional complexity for using error-and-erasure decoding is not very high. So if we go from binary decision to ternary decision, or from binary decoding to error-and-erasure decoding, it doesn't get horribly complicated. But also we have a large capacity gain. As you can see here, if we look at the binary symmetric channel, which is the green line here, then we go from the binary channel to a ternary channel, which is the green dashed line here. We have a pretty large capacity gain. However, if we further increase the quantization level to 4, then with the dotted line, we do not see that much capacity gain anymore, and we are already not far away from the binary WGN channel capacity. So that is that was the motivation that we will focus on error-and-erasure decoding. So this is our channel model. We consider a simple BPSK signal transmitted over binary AWGN channel, and conventionally we will make a binary decision like this, but now we introduce erasures for the bits that have too low magnitude, and the channel become like this. And now we have introduced error-and-erasures, we need a way to decode them. What we do is we use this specific error-and-erasure decoder, and we just call it EAD. And this EAD basically converts the error-and-erasure decoding to two steps of BDD decoding. How do we do this? So first of all, we need to replace the erased position of y with two complementary binary random vectors. Then we have no erasures anymore in y. We have two binary vectors, y1 and y2. Then we decode both y1 and y2 with the BDD decoder. Then we have two decoding results, w1 and w2. Then we will choose from them, choose one of them to be the final decoding decision of EAD. And we already analyzed the message passing decoding of EAD in our previous work. And you might be curious, what is the message passing decoding for product code and staircase codes? And we gave a little example here. So we show it with the one block of product code to be simple, and for staircase code it is similar. We consider BCH code as component codes, and the component code we call it DC. And then for a block of product code, we first start with the rows. We decode every row of the column with the component code decoder. Then we pass the decoding result to the columns. Then we decode all the columns with DC again, and we pass it back to the row decoders, and we do it so on and so forth. And this is an iterative decoding algorithm. And also, more specifically, this is what we call the intrinsic message passing for one block. And for in the next, we need to introduce the extrinsic message passing. And we first say that y is the row and column vectors of a block. Then we say for the same row and column, we say R is the channel output and DC is the component code decoder. So we recall that this was the intrinsic message passing for one row or column that looks like this. So basically we just decode Y with the component code decoder to get a decoding decision. Then is one step. Then for extrinsic message passing, we need to do some modification. We need to generate n vectors from y1 to yn. And what we do is we take the original vector y and replace the first bit in y by r1 and second bit in y by r2, and we go on like this until the last bit. Then we have y1 to yn, the n vectors, and we decode them with the component called decoder DC. Then we have n decoding the results. Then what we do is we take the first bit of the first decoding result, second bit of the second decoding result, all the way to the nth bit of the nth decoding result, and we combine them to obtain the final decoding decision of the EMP. As you can see that we would need to do n decoding steps per row or column, but what we saw is that for one thing, the EMP can be nicely analyzed with density evolution. For another, it also gives better decoding performance than the simple intrinsic message passing IMP. So naturally, we ask the question that if EMP is nice, can we somehow make it as simple as in IMP? So the decoding, the number of decoding steps, will make it them as low as in IMP. This is the problem that we study in our paper. So I reformulate the question a little bit. So we take y, which is here, and we take yk, which is the case vector in the EMP decoding we would need to look at, and we find that y and yk, they differ only by 1 bit. That is at the case position. For y we have yk, and for yk here we have the channel output. So we can the question that we look at can be boiled down to this simple research question, that is, if we have a word y and we know the decoding result of y, which is w, can we also know the decoding result of if we change 1 bit in y? So this question has been solved for binary symmetric channel in Zhang's paper, and we can always infer the EMP decoding result from the IMP decoding result just with some simple logical operations. But the problem gets more complicated for error-and-erasure channel, and that is what we did in this work. We want to generalize the simplification for error-and-erasure channels, and we will not show the details of the algorithm or the derivation because it's rather tedious, but instead we'll give a graphical illustration to give a general idea of how this can be done. So this is the space we are looking at. The WIMP, C1, C2, they are code words. And then we consider the BDD decoding. We know if the decoding result of y is WIMP, that we know the distance between y and WIMP should be smaller or equal to t, as we draw here. Then we change 1 bit in y, and we need to infer the decoding result. So there will be several cases. This is the first case. If we change 1 bit in y, and the distance between yk and WIMP may change, but here, if it is still smaller or equal to t, then we know the decoding result of yk will still be IMP. And this also applies for error-and-erasure decoding. That's a simple case. And the second case is now we change 1 bit in y we are now at yk, but yk is not in the hemisphere of any code words, then we will have a decoding failure. But the nice thing is, if we have a decoding failure, we will return the yk as the decoding result. And we know that the case bit in yk is actually the channel output rk. So we actually still know the decoding result. And this also applies for error-and-erasure decoding. The last case is now we are no longer in the hemisphere of WIMP, but in the hemisphere of C1, which is another code word. And theoretically, without decoding, we cannot know which code word C1 is. But we have the simple fact that if we change one bit in Y, it brings us closer to C1. That means that the case position in YK must be the same as the case position in C1. So then we know that C1K will be the same as RK. But this is not the same for error and erasure decoding, because if we have RK being an erasure, we do not know after the decoding to a 0 or to 1 will the erasure be resolved to. So that is the difficult part with error and erasure decoding. And we found that this is in general not able to, in general we are not able to solve it. But in the paper, what we did is we look at the case in more detail, and we found that some cases, even though they appear not solvable, but they can actually be solved. And that's what we did. And we, in this way, we can minimize the number of actual decoding steps. And this is the derived low complexity EMP algorithm, LCEA. And you can see that with the green lines, if we have the green lines, we would need to do redecoding, and which is not needed if you have a binary decoding. And here is the only additional complexity we would have. And we are not satisfied so far, and we really want to bring the complexity of EMP to be same as in IMP. What we could do is we can introduce the heuristic version of LCEA. What we do is we just use the heuristic value as the decoding result of EMP, where when the decoding result of EMP cannot be easily determined from the IMP result. And sometimes it's the IMP result, sometimes it's the channel output. And this way we can really reduce the number of decoding steps per row column to 1. And even it improves the decoding performance for some cases. This is the decoding result for even with subcode of BCH code with block length 511, and we have t equals to 3, so it can correct 3 bits error. And this is the EMP decoding result of the binary case. The performance is like this, and the complexity is here. The number of BDD steps, we normalize them to 1, and here it reduces because of early termination if the channel is good. And then we see this is the EMP with EAED, and we can see the decoding performance is now better, and the complexity is still several times higher than the binary case. But if we do not do any simplification, this will be actually 511 times the hard decision per case. And then we have the heuristic version. It further improves the decoding performance, and also we can see that the number of decoding steps is really similarly low as in IMP, because if we recall that each EAED consists of 2 BDD steps, so this is almost the same as the binary case. And note that we were not able to simulate any of the EMP algorithms before without the low complexity version of it that we derived here. And here are some more numerical results. We consider product codes. with small t, that's where the heuristic algorithm performs the best. So for product code with different rate, which is the x-axis, we show the decoding gain we get by using the EMP algorithms compared to the EMP algorithms on binary symmetric channel. And we can see that with the original EMP, we have some gain if we use error-and-erasure decoding, but if we use the heuristic version of the algorithm, we are even better. And so this brought me to the end of my presentation. In this work, we derived low complexity EMP algorithms, which enables us to use EMP in practice and also to simulate and analyze its performance. And also, we further proposed the heuristic modification of the algorithm, which further improves the performance for some codes and reduce the complexity. Also, we have some other results that I cannot cover in the talk due to time limit. We also derived the low complexity EMP algorithm for another error-and-erasure decoder. And we would like to stress the point that for error-and-erasure decoding, there are two ways to implement the decoding, which actually gave the different decoding results. And also we do a detailed analysis on the proposed EMP algorithms, and there are simulation results on more various product codes and staircase code in the paper. Okay, that was all of my presentation. Thank you very much for your attention.